Okay, here's an interesting theorem. There is something called the Gauss-Markov theorem, and it tells us if we think we have a model such that we have a random variable y and we have a row of predictors full and a vector of regression parameters as well as some error term epsilon. So in this model we're talking about y being a random variable that is potentially observable. We're talking about the epsilon being a random unobservable error. We have some predictor variables, explanatory variables, whatever we want to call them, and a vector of unknown fixed coefficients that describe the relationship between fixed x and random y subject to this error term. So we have this model, and the Gauss-Markov theorem tells us that if we assume that the expected value of these errors is 0, that they have a constant variance and that they are independent, then the Gauss-Markov theorem tells us that an estimator given by beta hat equals xtx inverse xty is a so-called blue estimator. So notice a couple of things in the notation. We now have observations on y. All of these are vectors or matrices as appropriate. Beta is a vector, x is a matrix, and y is a vector of now observed values of y. Then this estimator of beta is so-called blue, best linear unbiased estimator. Now that seems like kind of good properties for an estimator. We know how to compute this thing, and we also know many other properties of this. We know this corresponds to the least square solutions, a line or plane of best fit that minimizes the quadratic loss of the fitted values of the line from the data points y. Anyway, let's look at what we mean in this case by blue. Well, the first thing we're saying, we can explain quite simply, is the L blue. So we're saying we're talking about best linear unbiased estimator. So we said beta hat is equal to xtx inverse xty, and for the model we specified, these are fixed data points. This is a realization of a random variable. And if we have a quick look at what's going on here, we have a p by 1 vector. We have here an n by 1 vector. So this part here is actually p by n, n by p, p by 1. So this is basically a p by 1 matrix. So if we called that matrix C, just for some kind of notation, we have entries in C, C11, C12, all the way to C1n, and we have CP1, CP2, CPn, and we have these observations y1 through to yn. So what we're basically saying is that beta j is equal to c j1 y1 plus c j2 y2 and so on until we have a c jn yn. So beta j is just a linear combination of the observed random variables y with terms given by c, which is what we find from this matrix here. So it's a linear estimator. Now, because y are random variables, functions of random variables are random variables, y is a random variable, beta hat is a random variable. Unbiased. Okay then, the next term is this term unbiased, and in general for any estimator theta hat, to say that it's unbiased, what we're trying to say is that the expectation of theta hat is equal to theta, the fixed unknown population quantity that we're trying to estimate. So what we need to show is that the expectation of beta hat is equal to beta. So how do we get there? We need to find some kind of expression for beta hat that includes a beta. Well, we said that beta hat is xtx inverse xty, and we've said in our models that y is equal to x beta plus epsilon. Now remember, this is our statement of a model, but we insert this into our expression for the estimator. So beta hat is a realization of a random variable given by xtx inverse xt x beta plus epsilon. That's an expression that looks quite nice to factorize, so we'll factorize that down. Beta hat is equal to xtx inverse xtx beta plus xtx inverse xt of e. Epsilon, sorry. And in doing that factorising, we can see that there's scope here for a little bit of simplification, because this multiplied by this is an identity matrix. So the expression we end up with is a statement that beta hat equals beta plus xtx inverse xt of epsilon. So we now have an expression that gives us beta hat in terms of beta. The next thing we want to do is to take expectations of this. Okay, so we will shrink this out of the way a little bit and take the expectations. So what we're trying to find is the expectation of beta hat is equal to the expectation of beta plus xtx inverse xt epsilon. We've got a simple additivity that we can use here to break these two parts. So this is going to be the expectation of beta plus the expectation of xtx inverse xt epsilon, and of course what's the expectation of a constant? It's the constant. So we've got a statement that this is the expectation of beta plus xtx inverse xt multiplied by the expectation of epsilon. Now what we said very clearly in our assumptions at the start was that the expectation of epsilon was equal to 0, We didn't perhaps quite so clearly state that epsilon and x are independent, but the point of that is that when we take the expectation, this last part, that's a plus sign and that's a plus sign, but essentially this last part has expectation 0. So what we've shown here is that the expectation of beta hat equals beta. So we have a linear estimator, it's an unbiased estimator. Now, the last thing we'll look at here is the variance of beta hat. So we're going to go back and look at beta hat as we've given using this expression here. So if I start a new slide and put that expression in, we can see where we're following on from. We've said here that beta hat is equal to beta plus xtx inverse xt epsilon. So that's our expression for beta. So if we want to find an expression for the variance of beta hat, it's going to be the variance of beta plus xtx inverse xt epsilon. Now with a term there, we can apply some addition. So this will be the variance of beta plus the variance of xtx inverse xt epsilon, and, well, what's the variance of a constant? That's going to be 0. So what we're looking for is the variance of xtx inverse xt epsilon. Now, this part, as we've discussed for this model, we only contemplated this being constants. So what we need to do with the constant is bring them outside the variance, but we need to square it when we're doing that. And when we do that in matrix notation, when we're working with matrices, bringing something out and squaring it means pre and post multiplying. So we'll have a look at doing that. What we're saying then is that we want to find the variance of beta hat is going to be equal to xtx inverse xt multiplied by the variance of epsilon multiplied by xtx inverse xt, and this is all transposed. Well, we said at the start that under our big assumptions the variance of epsilon was constant and equal to sigma squared, so we can bring this out to the front. We can leave this part in, and then we can do a little bit of tidying here, because we can use our transpose of the products is the reverse of the product of the transposes rule, and we can basically bring this here and transpose it, and we can bring this here and transpose it, but of course it's symmetric, so it stays the same. And again, you can see instantly xtx inverse multiplied by xtx. These are going to give me an identity matrix. Identity matrix multiplied by something else gives me whatever we had. So essentially I'm saying the variance of beta hat is sigma squared multiplied by that matrix xtx inverse. Okay, so what we have to make assumptions on epsilon. such as zero mean, constant variance and independent, and if we make those assumptions, then the estimator given by beta hat is xdx inverse xty, then this estimator is the so-called best linear unbiased estimator. So we've explained what we mean by linear. This is just a simple linear function of y, the estimator. We've explained what we mean by unbiased, because we've shown that the expected value of beta hat is the quantity we're trying to estimate. We've also just shown that the variance of beta hat is given by sigma squared xtx inverse. What we haven't done is explain what we mean by best. And best means we could choose different estimators. We could find different estimators. Of those estimators, some would be linear and unbiased. But out of the possible linear unbiased estimators we have for beta in the model y equals beta x plus epsilon, out of the possible choices we have of linear and unbiased estimators, we don't find anything that has lower variance than this. So the best property tells us this is the lowest variance we can get amongst linear unbiased estimators. So we have a nice, to some people's mind anyway, theoretical property that we have linear unbiased estimators, and out of the class of possible linear unbiased estimators for this model, this is the variance as low as we can get it. What it means is for a given realization of a data set, for a given sample from a population, we now can make statements about the unknown betas in that population, because we know something about the properties of beta hat in terms of its expectation and variance, and these are the properties we need in order to be able to perform inference on the unknown betas.